Welcome to the presentation on developing a predictive model in GSTN. This presentation outlines the steps taken to pre-process a dataset and build an artificial neural network or ANN model to improve data processing in the goods and services tax network. The first step in the process is data loading. We start by importing the pandas library, which is essential for data manipulation and analysis. Next, we load both the training and testing datasets from CSV files. The structure includes xtrain and xtest, which contain the input features, and ytrain and ytest, which include the target variables. For context, a training set contains over 785133 samples. Now, we move on to data cleaning. First, the ID column, which is not required for analysis, is removed from all datasets. Then, we check for missing values in both xtrain and xtest. Additionally, we dropped column 9 due to the significant number of missing values, simplifying the dataset. Continuing with data cleaning, we replace null values with the median for specific columns. This replacement process is applied to both xtrain and xtest datasets. Afterwards, we verify that no missing values remain, ensuring the integrity of the data. In this slide, we focus on replacing null values with the median. For both training and testing datasets, missing values in columns like 0, 3, 4, and others were filled with the median of each column. This ensures the dataset is complete and no missing values remain after this step. In this step, we define a function to detect outliers using the interquartile range or IQR method. We identify outliers in both the training and testing datasets, which sets the stage for the next step, handling these outliers. In this slide, we revisit outlier detection. Using the function we defined earlier, outliers were identified in key columns of the dataset. This ensures that our data remains consistent and improves the accuracy of our predictive model. This slide focuses on outlier detection in both the training and testing datasets. The code shown prints the number of outliers for each column. On the left, we see the outliers in the training data, with significant numbers in column 0, 3, 6, and others. On the right, the testing data reveals a similar pattern. Detecting these outliers is essential for improving the model's accuracy by addressing any anomalies before training. After identifying the outliers, we handle them by creating a function to replace outliers with the median value. This is applied to specific columns to reduce the impact of extreme values on our model, improving the model's robustness. Here, we continue discussing outlier handling. By addressing outliers in columns 0, 5, 6, 7, 8, and 17, we ensure that our model is not skewed by extreme data points. This step contributes significantly to reducing errors in model predictions. In this slide, we address outlier handling by replacing them with the median value of the respective column. The code applies this process to both the training and testing datasets, specifically for columns with significant outliers like columns 0, 5, 6, 7, and others. This ensures the outliers are managed appropriately, preventing them from skewing our model's predictions. Once the data is clean and outliers have been addressed, we apply feature scaling. Using standard scaler from sklearn, we normalize the feature values to ensure that all features contribute equally to the model. This transformation is applied to both xtrain and xtest datasets. This slide demonstrates feature scaling using the standard scaler from sklearn. The scaler standardizes features by removing the mean and scaling to unit variance. We apply fit transform on the training data and transform on the test data. then convert the scale data into data frames for easier handling. Finally, we preview the scale datasets with .head. Now, let's look at the artificial neural network model architecture. First, we import the necessary libraries from TensorFlow and Keras. The model design includes a sequential model with 21 neurons in the input layer, 2 hidden layers, 64 neurons in the first, and 32 neurons in the second, both using ReLU activation, and a final output layer with 1 neuron using sigmoid activation. The model is then compiled using the Adam optimizer, binary concentropy at the loss function, and accuracy as the evaluation metric. After the architecture is defined and the model is compiled, the model is trained, and we achieve an accuracy of 97.49%. This demonstrates the model's effectiveness in predicting outcomes in the dataset.